So let's look at Web API hacking methodology. Uh, some new points which I was not aware. Web-based APIs can be used by mobiles and IoTs as well. These devices frequently communicate with back-end web servers via APIs. Coming back to hacking methodology, to hack an API, attackers needs to identify the API technologies, security standards, and attack surface for exploitation. Four phases. So identify the target, detect security standards, identify the attack surface, and launch attack. So identify the target. Before hacking an API, an attacker first needs to identify the target and its perimeter. So in identify the target, there are two sections: HTTP and message formats. APIs such as SOAP and REST mostly use the HTTP protocol for communicating API based messages. The HTTP protocol is a text based protocol where the header information is transmitted in a readable format. For example, consider the following HTTP request and response headers. So here, this is an example of a HTTP request header. It contains a request line, request header, request message header, blank line separating the header and the body, the request message body. So HTTP response contains the status line. First line is the status line, and then it contains the response header, then response message header, blank line separating header and body, response message body. As shown in the figure, both HTTP request and HTTP headers are transmitted in plain text. An attacker can easily manipulate these headers to identify the target. So within identify the target, the second section is message formats. The API messages transmitted over the web will take some format such as JSON or REST API and XML for SOAP API. If these formats are used incorrectly, they can pave the way for vulnerabilities. As these formats are easy to understand, an attacker can easily manipulate messages encoded in these formats to identify the target and its perimeter. So after identifying the target, detect the security standards. APIs such as SOAP and REST implement different authentication authorization standards such as OpenID Connect, SAML, OAuth 1.x and 2.x, and AWS security. SSL provides transport level security for API messages to ensure confidentiality through encryption and integrity through signature. Although SSL is used for security, in most API messages, only sensitive user data such as credit card details are encrypted, leaving other information in plain text. So, if these security standards are configured improperly, an attacker can identify vulnerabilities in these standards for further exploitation. So, after identifying the target and detecting the security standards, the third step in API hacking methodologies identify the attack surface. So an attacker needs to identify the attacker surface for launching the attack. Note that there will not be any UI for API to identify attack surface. We can only see the API endpoint. To identify an attack surface of an API, attackers need to understand the API's endpoints, messages, parameters, and behavior. Use the following techniques to identify the attack surfaces of the target API. API metadata vulnerabilities. API metadata reveals a large amount of technical information such as paths, parameters, and message formats, which is useful for performing an attack. REST API uses metadata formats such as Swagger, RAML, API Blueprint, and IO docs, while SOAP API uses WSDL, XML schema, etc. For example, consider the following code snippet of Swagger that reveals technical information. Note, Swagger is a suite of tools for API developers. So attackers can exploit vulnerabilities in these definitions to perform various attacks on APIs. So this is an example of a swagger. So you can pause the video and look at this code to get the more information. Example of a swagger definition. So as you can see, first the path is identified here, which is a point of attack. HTTP method or other methods handles correctly. So here the method is delete, and then both two or tokens enforced and validated correctly. And then we have parameters, name, description, required type, parameter type, allow multiple. So is acts in the parameter. What if we send a multiple or none at all? So allow multiple is set to false. If we send a multiple, what is the behavior? So these kind of examples for the metadata vulnerabilities. So API discovery, in the identify attack surface, we saw API data metadata vulnerabilities, then API discovery. Even if an API does not have metadata, attackers monitor and record the communication between API and an existing client to identify the initial attack surface. My understanding of how to obtain metadata example only is given below after going through the description given in Aspen book. An attacker uses mobile that use the API, configures a local proxy to monitor traffic, and the mobile will be configured to use this proxy. Then using some automated tool, the metadata can be generated. The key here is it is generated even if it is not available. So the metadata can be generated if it is not available by using a proxy. Then identifying the attack surface using brute force. If none of the above mentioned techniques works, the attackers try to identify the API paths, arguments, etc. through brute forcing. Common API paths used by developers include API, API v2 slash APIs.json, etc. Furthermore, some APIs such as Hypermedia allow retrieving links and parameters related to an API response. This information helps attacker to identify the attack surface. Launch attack. After identifying the target API, analyzing the message formats and security standards, and identifying the attack surface, the attackers perform various attacks on the target API to steal sensitive information such as credit card details and credentials. So in the attack, the first attack is fuzzing. So attackers use fuzzing technique to repeatedly send some random input to the target API to generate error messages that reveal critical information. To perform fuzzing, attackers use automated scripts that send numerous requests with various combinations of input parameters. Attackers use tools such as Fuzz API to perform fuzzing on the target API. Fuzz API is a tool to perform fuzzing on the API. Invalid input attacks. In some scenarios, fuzzing is difficult to perform due to its structure. In such cases, attackers will give invalid inputs to the API, such as sending text in place of numbers, sending numbers in place of text, sending a greater number of characters than expected, and sending null characters, etc., to extract sensitive information from unexpected system behaviors and error messages. Malicious input attacks. After fuzzing invalid input attacks, third one is malicious input attacks. In the attack discussed above, attackers try to retrieve sensitive information from unexpected system behavior or error messages. A more dangerous attack is where the attacker injects malicious input directly to the target, both the API and its hosting infrastructure. To perform this attack, attackers employ malicious message parsers using XML. The following code snippet illustrates an XML bomb attack. The following is also called as a billion laugh attack. As you can see in the XML, there are a lot of ampersand LOLs. An XML bomb is small but dangerous piece of code that is written and sent with the intent of crashing the targeted server or program that tries to read and decode it. When an XML parser tries to process an XML bomb, the nested data entity starts growing exponentially. Another way in which attackers perform this attack, that is malicious input attack, is by uploading malicious script files. Example, by uploading shell script instead of PDIC document. This may result in executing the malicious script to bypass the security mechanisms on the server or propagating the script to other parties who are trying to access the API. Using this technique, attackers try to extract information related to underlying file system. So fourth type in the launch attacks is injection attacks. Similar to traditional web applications, APIs are also vulnerable to various injection attacks. For example, consider the following normal URL: BillPay API v1 cust 459. For the above mentioned URL, the API retrieves the customer details based on customer ID 459 from the database using the following SQL query. You can see the query here. In the above mentioned URL, assume that the attacker injects a malicious input as shown here. The resultant malicious query will be select from customers where customer ID is equal to blank or 1 equal to 1. The above mentioned query returns details of all customers in the database. Using this information, an attacker may further delete or modify the data in the databases or use the customer's information to perform other malicious activities on the database server. These API injection attacks are performed not only on SQL, not only using SQL, but also using JSON, JavaScript, XPath, XSLT, etc., which require parser processors for execution. Note, similar to injection attacks, web APIs are also vulnerable to cross-site scripting and CSRF attacks. So, okay, then the next attack is exploiting insecure configurations. So within insecure configuration, we have insecure SSL configuration, insecure direct object references, insecure session authentication handling. So insecure SSL configuration. Vulnerabilities in SSL configuration may allow attackers to perform MITM attacks. For example, using self-signed SSL certificates for secure API access may allow attackers to perform MITM attacks. An attacker may sniff the traffic between an API and client, manipulate the client-side certificate, and start monitoring or manipulating the encrypted traffic between client and API. Note, in cryptography and computer security, self-signed certificates are public key certificates that their users issue on their own behalf, as opposed to certification authority issuing them. These certificates are easy to make and do not cost money. However, they do not provide any trust value. For instance, if a website owner uses a self-signed certificate to provide HTTPS service, people who visit that website cannot be certain that they are connected to their intended destination. For all they know, malicious third party could be redirecting the connection using self-signed certificate bearing the same holder name. The connection is still encrypted but does not lead to its intended target. Note, when you type a URL or follow a link to secure website, Your browser will check the certificate for the following characteristics. The website address matches the address on the certificate. The certificate is signed by a certificate authority that the browser recognized as a trusted authority. So, in exploiting insecure configuration, we saw insecure SSL configuration. Now we will see insecure direct object references or IDOR. In general, direct object references are used as arguments for API calls, and access rights are not imposed on the objects for which a user does not have access. These vulnerabilities can be identified through API metadata and exploited by attackers to identify the parameters and try all possible values for the parameters to access the data to which the user does not have access. Insecure session authentication handling. This is similar to session hijacking. Vulnerabilities such as reuse of session tokens, sequential session tokens, long session token timeout, unencrypted session token, and session token embedded into a URL allow attackers to hijack and take over the client session and steal or manipulate the message between client and API. So please note that insecure session authentication handling is somewhat similar to session hijacking. Next, after looking at the exploiting insecure configuration, we'll see login credential stuffing attacks. Login credential Login or credential stuffing attack. Note: credential stuffing is a subset of the brute force attack category. Brute forcing will attempt to try multiple passwords against one or multiple accounts, guessing a password. In other words, credential stuffing typically refers to specifically using known username password pairs against other websites. Credential stuffing attack exploits the tendency to reuse passwords and usernames across different accounts. Attackers generally employ bots for different login attempts. So, next type of attack is API DDoS attack. Note: rate limiting is used to prevent users overwhelming your API with requests, limiting denial of service threats. Attackers can carry out these attacks using botnets that are created to discover and stay within the API rate limit control to increase the possibilities of an attack. Along with the regular traffic from legitimate users, attackers' request can also bypass API security management functions, load balancers, and other security implementations. Most of these attacks may not be volumetric. They may also exploit certain API vulnerabilities to disrupt the API services. For instance, an attacker who gains access to the API can consume the CPU and other memory resources reserved for the API to delay the service for as long as possible. Next attack is authorization attacks on API, OAuth attacks. According to OAuth.com, OAuth is an authorization protocol that allows a user to grant limited access to his or her resources on one site to another site without having to expose his or her credentials. OAuth grants authorization flows for many computing devices and applications, such as connecting users to different applications from one application to access the required information. Note: OAuth is not same as SSO, even though they look functionally similar. As you see in the diagram, a user in the first step, the user has entered username and passwords to a third-party website. The credentials used to access the data are sent to website with users data. Example: Facebook. So the Facebook will be used to authorize the third-party website. Figure in olden days, this is what used to happen. The third-party website was getting username and password of Facebook, which obviously is not secured. So To overcome this issue of sharing authentication details with the third-party website, OAuth has something called as grant type. It has two types, implicit and authorization code grant type. So in the figure, if you see the user as given the username and password to third-party website. So in this case, he is revealing the authentication details to a third-party website. The username and password belongs to Facebook, which is shared with the third party. So if you see here, the implicit grant type, um, you can pause the video and look at the diagram. And here the client first sends authorization request to OAuth provider or authorization server, not directly but via user agent. It is sent as a GET request shown below. Here authorization is an API that is used by client. In the example shown above, authorization is an API that is used by the client. Sometimes it could be slash auth only. Client ID, redirect URI are all parameters. So client ID lets the authorization server knows who is the who is requesting for the authorization. So the response to the authorization to be sent to redirect URI. In this example, the OAuth has to send the response to the callback. Since this implicit the client is asking OAuth to send the token as a response type. Token is secret key that will give the access to confidential data for client application. Via scope parameter, the client is asking the access to items that are set to scope. In this example, it is asking for OpenID and profile of the users. State is like a unique ID for that transaction. This changes for every transaction and is optional, so vulnerable. This is the second step for implicit grant type. In the first step, the client sends authorization request to OAuth provider or OAuth authorization server, not directly but via the user agent. So this is second step for implicit. In the second step, once the OAuth provider receives the request sent in the step 1, it will redirect the user login page and ask the user's consent. This login may be Google account or Facebook account, and these credentials will not be shared with the client application. Third step, the OAuth provider issues an access token grant to client via user agent. This token grant is important. If it is lost or stolen, then it has potentiality of accessing the user data on OAuth provider. The OAuth will use the redirect URL specified in step 1. So the client application has to verify the state number provided by OAuth shown above, and it has to match with one given in step 1. The access token will pass through the web browser, and whoever has access to browser can view this token. As already explained in step 1, this state is not enforced, it is optional. So once the client receives the token, it will issue the API call through the browser again to OAuth. The OAuth responds with resource grant and sends the response containing whatever was requested in previous step. Since client sent user info in the previous step, the response will contain information like user's email ID, username, etc. As we saw in the above 5 steps, in implicit grant, everything passes through browser, never direct communication between client and OAuth provider. This means the access token, API call and resources, even though are encrypted, it has to be decrypted by browser and sent to client or OAuth. Authorization code grant, like implicit grant type, the step 1 is almost same, but the respond type is code, not token. The difference is the token is used to access the resource, whereas code is to say that you are eligible to get a token. Later on, the token will be given. Step 2 is exactly same as implicit grant type, that is user login and consent. In step 3, instead of returning access token, authorization code is sent. Step 4, after getting the authorization code, the client application connects directly to OAuth provider. This connection is called as back channel. It requests for access token now. It gives another redirect URL to get the access token. Step 5, now the OAuth responds with access token directly to the client. Next two steps are almost same as implicit grant type. So different steps, different actors involved in the OAuth process. Owner of the resource. The resource owner, also known as a user who grants permission to an application to access his or her account. The access to the application is limited or conditional, such as providing only read and write permission. Authorization resource server API. The resource server provides the secured user account, and the authorization server validates the user identity and then supplies the access token to the application client or application. It is an application that seeks access to user account. To access the account, the user must authorize the application. Then the API should validate the authorization. Various attacks on OAuth performed by manipulating the requests stated above are discussed below. Attack on connect request. Most sites enable users to access other websites such as LinkedIn, Instagram, and Twitter via OAuth. An attacker can exploit requests to connect one site to another. That is, when the user hits the login with the connect button, then he or she can gain illegal access to the client side or user victim's account by connecting his or her account to provider's website. Steps to perform an attack on connect request. The attacker opens a fake account on the provider's website. The attacker initiates the connect operation with the client through his or her fake account on the provider's website, but halts the authorization server redirects, which means that the attacker validates the client to access his or her resources on the provider while the client is not informed. The attacker creates a malicious web page as follows. Use a CSRF to make the user log out on the provider. Again, use a CSRF to make the user login on the provider using his or her fake account credentials. Spoofs the first request to connect the provider account with the client. It is just another GET request. It is usually performed inside iframe tag to make the user unaware of this action. Once the victim opens the attacker's malicious page, his or her account gets logged out on the provider and connects as fake account. Then the attacker's fake account is connected with the victim's account on the client. The victim does not ask the client for permission as the attacker has already approved it. Hence, the attacker can log into victim's account on the client side using his or her fake account on the provider. Attack Attack on redirect URI. While registering, the domain is usually specified by the client and only those redirect URI and the specific domain are permitted. If an attacker can identify vulnerabilities such as excesses on a web page on the client domain, he or she can exploit them to capture the authorization code. Steps to perform redirect URI. The attacker leaks data through a vulnerable page on the client domain. The attacker installs malicious JavaScript on the page. Then the page sends the URL, which is loaded in the browser, to the attacker. The attacker creates a page that prompts the user to open a malicious link. When the victim opens the malicious link, the user get agent is redirected to XYZ, and the code is then exfiltrated to the attacker. Now the attacker uses the retrieved code to provide access token via authentic redirect URI such as this. A CSRF CSRF on authorization response. The attacker performs a CSRF. The attacker performs a CSRF attack to connect a fake account on the provider with victim's account on the client side. This attack exploits a third request related to authorization code grant. Steps are as follows. The attacker opens a fake account on the provider. The attacker starts a connect operation with the client through his or her fake account on the provider, but halts the authorization server redirects, which means that attacker has validated the client to access his or her resources on the provider, while the client is not informed. Hence, the attacker stores the authorization code. The attacker persuades the user to send a request to the website. This operation can be implemented by luring the victim into opening a malicious link embedded with an image or script tag along with the above-mentioned link as source. When the victim logs into the client, the attacker's fake account is connected to the victim's account. Now the attacker can sign in as the victim on the client by logging in with his or her fake account on the provider. Access token reusage. OAuth requires unique access tokens for individual clients. It ensures that these tokens saved on the authorization server are mapped to relevant scopes and time expiry. Access tokens provided for client A can work for client B. Attackers exploit this feature to perform attacks on clients that allow grants implicitly. Steps to use access tokens. The attacker develops a legitimate connection the attacker develops a legitimate client application client A and enrolls it with some provider. Now the attacker lures the victim into accessing client A and gains illegal access to victim's access token on client A. Let us consider that the victim access client which uses the implicit grant. In such case, the authorization server redirects the user agent to this URL. Now the attacker can open this URL with client's access token. The attacker is verified as a valid entity by client. Therefore, one access token is sufficient for use on the many clients using implicit grant. So after authorization attack on API using OAuth attacks, let's see REST API vulnerability scanning. REST API vulnerabilities introduce risks that are similar to web applications, such as critical data theft and intermediate data tampering. Performing thorough scanning on REST APIs can expose various underlying vulnerabilities that the attackers can exploit. Attackers can use tools such as Astra to carry out REST API vulnerability scanning. Astra allows attackers to detect REST APIs that are vulnerable to attacks such as XSS, SQL injection, information leakage, CSRF, broken authentication, and session management. In the above screenshot, we can see Astra has detected CORS misconfiguration as the vulnerability. REST API vulnerability scanning tools, Fuzz API, W3AF, App Spider, Wookie, VOOKI, WASP Zap. So bypassing IDOR via parameter pollution. So insecure direct object reference IDOR is a vulnerability that arises when developers disclose references to internal data enforcement objects such as database keys, directories, and other files that can be exploited by an attacker to modify the references and gain unauthorized access to data. For example, consider this normal request API xyz.com/profile/user ID is equal to 321. The attacker manipulates the above request using parameter pollution to bypass IDOR api.xyz.com/profile/user ID is equal to 654 and user ID is equal to 321. So in the next video, let's see web shells.